Hello, guys. Welcome back. Happy New Year, everyone. Welcome to another exciting episodes on mechanics. Maybe further mechanics or just normal mechanics. All right, let's get going. All right, welcome back. This is our first questions for the past year paper, June 2020, paper 43. Let's read it through before we start. Now here you have particle P and particle Q as shown in the diagram here. Now, each one of them has a mass of m kg and 0.2 kg respectively. And then P is projected at a speed of 2 meter per second towards Q, which is stationary initially. Now, after the collisions, P and Q move in the opposite directions with speed of 0.5 meter per second and 1 meter per second. All right, now I'd like to show you how the motion actually look like before we get started with the um, mechanics solution. All right, now let's take a look at before collision. Uh, what will we get? Okay, you can see that P is projected towards Q. Yes, for sure they're going to collide in this case. And then what will happen after the collision? Let's take a look at the second video here. Right, you can see that P, Q collide, and then after that they will move in the separate or opposite directions. P would move in the opposite direction with a speed of 0.5, whereby Q will be moving in the opposite directions to P at a speed of 1 meter per second, respectively. All right, now let's take a look at how do we actually solve this mechanics problem here. Now, to solve any mechanics problem, we have to choose the right tool for the right context here. Now, since we are dealing with collision, so there are two simple rules to follow in the exam. Now, the first one will be conservation of momentum. Secondly, we have to rely on Newton's restitution law, right? But for mathematics 9709 syllabus, they don't cover Newton restitution law, right? So here, it's quite safe to just rely on conservation of momentum, right? Now, just to recap, conservation of momentum state that the total momentum of a closed system remain constant. Basically, it means total momentum before collisions and after collisions must be the same, provided there is no external force acting on the system. And then the system that we are looking at here just consists of two particles, P and Q. So that's a system that we are looking at. And then there is no other external force acting on these particles, P and Q, right? So let's get started. Now, by using conservation of momentum, I'm going to write down the concept. So the concept that we're going to use is conservation of momentum. And then conservation of momentum state that total momentum before. Let's look at how do we calculate total momentum before. Now, total momentum before collisions. So maybe it's best if you write down the total momentum before collision must be the same as the total momentum after collision. All right. Now, the total momentum before collision, let's look at this diagram here. That will be momentum is given by the product of mass and its velocity. So we have for P, we have a mass of m, and then its velocity is 2 meter per second. Now, bear in mind, whenever you deal with conservation of momentum, since momentum is a vector quantity, therefore directions is critical in this case. Now we always make trivial assumptions. The directions to the right, we assume that the momentum to the right is assumed to be positive, whereby the momentum to the left will be otherwise negative in this case, right? So by using these rules and guideline, the total momentum before collisions would be m multiplied by 2, of course, plus 0.2 multiplied by 0 meter per second, because initially q was stationary. And then it must be the same as the total momentum after the collision. Now, after the collisions, we can see that P is actually moving in the opposite direction. These directions, whereby Q is moving in the opposite direction. You can see that the directions of Q is in the same directions with our assumptions here. So therefore, Q would have a positive momentum, whereby P would have a negative momentum in this case. All right, now using that, that will be m, because p is moving in the opposite directions um, to the directions that we have assumed here. So therefore, it will be negative 0.5 meter per second instead. And then we are going to add up the momentum um, produced by q. Q is 0.2 kg, and then multiply with its velocity in the same directions as the assumed direction. So therefore, in this case, we have this. And then by solving this, we will have 2.5 m. Okay, I'm going to move this over here. You have a 0.2 here. And then from here, we will get m is equal to 0.08 kg. The unit for this is kg, since all of them have the unit of kg here. And then there you have it. That's how we find out the missing mass for particle P using conservation of momentum. All right, now I hope that is clear. I will move on to the next questions shortly. All right, see you shortly. All right, welcome back. This is our second question. Okay, as usual, we're going to read it through before we try to attempt to solve this. Okay. Now here for this second question, we have a minibus of mass 4000 kg. It's traveling along a straight horizontal road as shown in the diagram. The resistance to motion is constant, opposing at 900 Newton in the opposite directions of the driving force. Now, the first questions, we need to find the driving force when the acceleration of the minibus is 0.5 meter per second square. Okay. And then the second one, we need to find the power required for the minibus to maintain a constant speed of 25 meter per second. All right, let's take a look at how to work this out. Now, before that, just let me show you how the motion would look like in this case. Okay. It's a very simple motion here, you can see. So due to the um, uh, driving force imposed by the engine, the car, oh sorry, in this case it's not the car, it's a minibus. So the minibus will be able to move forwards. The driving force must be larger than the resistant or resistive force in this case. Now the resistive force in this question here, now, most probably will be consist of its frictional force and air resistance. Even though for a short durations of traveling, the air resistance may not impose a lots of resistance towards the motion of the minibus, but yet the frictions will, right? So I just like to make it clear, the resistance here actually refer to both the frictional force and the air resistance. All right, now since we know how the motion looks like, let's take a look at how to answer question number A, 2A. Now again, we're going to pull out mechanics tools that we can use, or the concept. Now, since this is dealing with forces and motion, Newton's second law would be appropriate to solve this problem here. Now, Newton's second law states that acceleration is directly proportional to its resultant force. bear in mind, is directly proportional to its resultant force. So based on Newton, we are looking at A here. So the concept that we're going to use here will be Newton's second law. Okay, now the accelerations is directly proportional to the resultant force. Okay, now in terms of equation wise, we can always write as MA, all right, where the M is the mass of the minibus in this case. Now, since the minibus is moving at the accelerations of 0.5 meter per second square, right? Now we would be able to find its driving force. Now, first of all, resultant force. How do we get the resultant force in this case? Resultant force basically means the difference between all the forces that is acting on that object itself. So in this case, we only have two forces that is acting on the minibus. That is the driving force and the resistive force. So therefore, the resultant force would be the difference between these two forces. Okay, I would like to assume that in this case, the driving force must be larger than the uh, resistant force. So therefore, we will write down the driving force must be larger than the resistant force. Okay, so this is the difference between the two forces. And then the difference between these two forces would produce an accelerations on the bus itself. And then the bus is having a mass of 4,000. We knew that the bus is moving at 0.5 meter per second square in these directions. Okay, so the acceleration is 0.5 meter per second square here. Right. So from here, we will be able to find out its driving force, which is quite direct. You'll get 2,900 here, Newton. So the driving force for the minibus, in order to maintain a constant acceleration of 0.5 meter per second square, is 2,900 Newton. All right. Hope that is clear at this point. Okay, let's move on to B now. Now find the power required for the minibus to maintain a constant speed of 25 meter per second. All right. Now, if the bus were to maintain a constant speed, it means that there will not be any acceleration. So, therefore, we're going to write down some um, conclusions that we can get from the constant speed itself. So, since the bus is moving at a constant speed of 25 meter per second, therefore we know that its acceleration A in this case must be equal to 0 meter per second square instead of 0.5 meter per second square from the first question here. So now the acceleration is 0. Sorry, it's a 0 meter per second. Right? So I'm going to erase this. Instead of having 0.5, it should be 0 meter per second square now. I mean that is maintaining its speed uniformly. And then by using Newton law one more time, so we're going to apply Newton's second law again. Now, of course, in the exam, you don't have to explicitly state the law, but you have to know the formula that you are supposed to use to actually solve this, right? So by using Newton's second law, we know that the resultant force must produce an acceleration in this case. So the same formula that we're going to use here. The only difference is the acceleration now is 0. So therefore, the resultant force must be equal to 0 Newton. And then we know that the resultant force, uh, the difference between the resultant force, the difference between the driving force and the resistant force is given by this, and that should be equal to 0. Therefore, we know that the driving force must be equal to 900 Newton in order for the minibus to be able to maintain a constant speed of 25 meter per second. Right? All right. Now that's the first part of it. The second part for B is we are asked to find the power required. Right now, the power Using the formula for power, P is given by the force multiplied with its instantaneous speed in this case. Now, the force that we are referring to here is the driving force because that's the force that is going to produce by the minibuses. So therefore, in this case, we can write down the power is given by the driving force multiplied with V here. And then the driving force that we are having here for the minibus to be able to maintain a constant speed is 900 Newton multiplied with its constant speed 25 here. So that would actually give us 22500 watts, or you can actually write it down as 22.5 kilowatts if you want to use prefix methods. And then there you have it. That's the solutions for um, second question here. All right, now I hope that has been helpful to you. I'm going to move on to the third questions shortly. All right, welcome back to our third question here. This is questions about equilibrium. All right, let's read it through first as usual. Now we have four core planar forces of magnitude 40 Newton, 20 Newton, 50 Newton, and F Newton acts at a point in the directions shown in the diagram there. Now the four forces are in equilibrium. Now the word core planar basically means it's a two-dimensional forces. It does not appear in a three-dimensional, right? So just in case you're wondering what is core planar. Right? Now the questions state that we need to find the missing magnitude of the F and the angle alpha as shown in the diagram there. Now because all the forces are in equilibrium, therefore we can apply Newton's second law one more time. Now Newton's second law states that the resultant force is directly proportional, sorry, the acceleration is directly proportional to its resultant force. Now since the forces are in equilibrium, therefore the resultant force must be equal to zero. Now that's our main concept here. Sorry, that's our main concept. All right. Okay, let's look at this. So the main concept would be by using Newton's second law. Uh, we know that the resultant force is equal to ma. Alright, now whereby these four forces are in equilibrium, therefore the resultant force must be equal to 0 Newton here. Now, how do we obtain the resultant force? This is the big deal here. Right? Now, in order to work out the resultant force, it's better if we apply vector 2 here, since it's two-dimensional. If it is a one-dimensions force, then we don't have to worry too much about vector here. Right? So instead of using um, this Newton's second law, F net equal to ma, we can actually write this, the resultant vector for the resultant force is directly proportional to its resultant acceleration, right? Now for the system to be equilibrium, now therefore it must be 0 Newton. Now first of all, we're going to work out the force in the vector form for each one of these individual forces. Now the first one, 20, the force 20 Newton, we can represent it as a vector here. I'm going to write it down here. So we can write as 50 cos 45, because if you were to draw a right-angled triangle here, okay, I'm going to show it to you, right-angled triangle. Now the x component for this force 50 Newton is given by 50 cosine 45. Now if you assume that this is like your Cartesian coordinates, for instance, if you assume that this is like your Cartesian coordinates, and then this is your y, this is your x, for instance, then therefore Since 50 Newton is on the third quadrant, so therefore it must be a negative. Right? So this direction must be negative. And then now the y component for this force 50 Newton is written as, because it's in the third quadrant also, so therefore there will be a y sine 45. So overall, we can represent this force in its vector form like this. And then, of course, you can simplify this later on. If you simplify this, this would actually give you a negative 25. Let me see. Is it negative 25? Yeah, correct. So it's negative 25 sub 2, and then negative 25 sub 2. Yeah. All right. Now that's how we represent the force of 50 Newton in the vector form. Now the first part. Next, we're going to look at the second force, 20 here. Okay. Now we're going to perform the same procedure here. We're going to draw a right angled triangle, and then we're going to work out the x component for this force, which is given by 20 cosine 30 degree. Okay. Now because it's in the fourth quadrant in this case, the x component is positive because this x is positive, but is moving downwards for the y component. Now the y component is negative 20 sine 30 here. And then there you have it. That's how we represent the vector 20 Newton, the force 20 Newton in its vector form. And then of course we can simplify this. We can write as now this one will be a sub 3. This, if you press your calculator, it should be sub 3 over 2 here. That will be a 10 sub 3, and then sine 30 is a half, so therefore negative 10. Yeah, of course, make it a habit. This is a Newton. Sorry, this is a force, so it must have units of Newton here. All right. Now we are done with representing both forces using vector form. Okay, so now we're going to work out the force 40 Newton in its vector form. So that we can write as, okay, just let me write down here. 40 cos 60, and then for its vertical component, will be 40 sine 60. All right. And then there you have it. Of course, you can always simplify this. If you were to simplify this, you will get 20, and then this one will be 20 sub 3 here, Newton. All right, and then there you have it. And then for the last one, okay, for the last one, we can also represent the unknown force in its vector form. So we can write this as, this is much more easier because no calculation is needed here. So we can just write down f cos alpha, and then f sine alpha here. But bear in mind, based on this orientation, we notice that the f is in the second quadrant, so the x component must be a negative, so that must be a negative f cosine alpha, and then whereby the y component is positive. So that's how we represent the force f in its vector form. All right, now we are ready. Once we have obtained all these forces in its vector form, now we are going to apply the Newton's second law concept that we have laid out here. Now before that, I'll just label this as F1, for instance, and then this one I'll label as F2, and then next one I'll label as F3, and then lastly I'll label this as F4. And then resultant force equal to 0 means we have the summation of all these vector, because the vector has already carried its direction, so we don't really need to worry about whether we are supposed to subtract or whether we are supposed to perform summation and so on. So resultant force here all refer to the sum of all the forces. So resultant refer to the sum of all these forces. That is the sum of force 1 uh, add up with sum of force 2 and then add up with the sum of force 3, and then finally we're going to add up with force number 4. And then the total or the sum of these forces or the resultant force must be equal to 0 Newton. Okay, now all we need to do is just substitute all this value in here. So we have 25 sub 2. So just let me put it down here. I will have my F2 here, and then my F3, my F4, and then this would all yield 0 Newton. Okay, now to solve this is quite direct. All we need to do is just extract its horizontal components. So its horizontal components, we have F cos alpha must be equal to, we have here negative 25 sec 2 plus 10 sec 3 plus 20 here. Now that's what we are supposed to have. And then that will be our first equation here. All right, now these equations is not very tough to solve. All you need to do is just key in this particular value into your calculator. Now, if you key in this correctly, you should have, let me see, you should have 1.965 in total. So all this result is 1.965 here, right? So you can check with your own calculator on this. And then whereby the vertical component f sine alpha, now that will be 25 sec 2 plus 10 minus 20 sec 3. Okay, so in this case you will get a larger value, which is 10.714 if you want to leave it to 3 decimal places. Okay, now finally we're going to use all this result to obtain our magnitude f. All we need to do is just solve these simultaneous equations. Now to get the f, we can square equation 1 and equation 2 here. So we can square this one and square this one. The main reason why we do this is because we want to make use of one of the trigonometry identity, which is, so the identity, I just write it down here. So one of the trigo identity. Okay, the trigo identity is sine square theta plus cos square theta is equal to 1 here. So if you sum up the square of all this, you will end up with f square sine square alpha plus cos square alpha should be equal to 1.65 square plus 10.714 square. Alright, so that's what we have. And then all you need to do from here is just finalize the value for f. Shouldn't be that tough. So your f is just the square root of this summation here. Okay, so if you use your calculator, you should be able to obtain the value for f in this case. All right, so this value I leave it to you. You can use your calculator to find out. And then finally we're going to figure out the alpha itself. So the alpha itself is, you can also make use of trigonometry ratio. Okay, so the trigonometry ratios that we have would be, here you can take 2 divided by 1 instead. So you can take equation number 2 divided by equation number 1. We will end up with tangent alpha. So tangent alpha is 10.714 divided by 1.965 there. And then from here, we will be able to obtain its um, angle alpha by taking the inverse tangent here. Okay, based on my calculated value, it should be 79.6 there. All right. So before we end, just let me check whether all this value is uh, correct. So let me check 1.965. Okay, so we have a square here, 1.965, add up with 10.7714 by 10.714. Okay, so that's what we have, and then we're going to square root that. Okay, uh, 118.651. Okay, let's okay. So I would say that roughly this value for f will approximately 10.9 if you leave your answer to the nearest three significant figures. But then again, by all means, use your calculator to check it on your own. Right? But the concepts are here. Right? Now I hope these questions has been helpful to your revision. All right. Now I'm going to move on to the next question shortly. All right. Question 4. Okay. Now let's read it through before we get started. A car starts from rest and move in a straight line with constant accelerations a meter per second square for a distance of 50 meter. Now the car then travels with a constant velocity uh, of a certain value, which is not given, but the car is travel with a constant velocity for 500 meters for a period of 25 seconds there. Now, before decelerating to rest, the magnitude of this deceleration is 2a, which means it decelerate more than its acceleration. Okay. Now, let's take a look at how we're going to work with this. Now, A, sketch the velocity time graph. Now, in order to sketch the velocity time graph, there are two things you need to remember about this graph particularly. Now, first of all, this graph represents speed, or sorry, velocity and time with respect to time here. As time progresses, what will happen to the velocity? And then there are two extra informations we can obtain from this graph. Mainly, the first one is the acceleration. So the gradient of this graph of the velocity time graph represent acceleration, whereby the area under the graph represent uh, displacement in this case. So I hope that is clear. Let's look at how to roughly sketch the motion of this car here. So it's moving at a constant acceleration. Constant acceleration means a straight line in this case for a distance of 50 meter. All right, now I have no idea how long this is spent to actually move 50 meters. So we're going to roughly um, get an idea here. All right. So take for instance, in this case we have, okay, because it's moving at a constant speed. So constant speed mainly means constant speed would means a straight line. Okay, so it's a straight line. So we can roughly place it somewhere here, even though we are not very sure of the um, distance. We are not very sure of the time, sorry, but we know that the area under this line here. So just let me roughly mark it here. So the area under this triangle represent 50 meter, and then the gradient of this graph represent a meter per second. So its acceleration is a meter per second. Uh, it should be able to reach speed up to here, v here. Okay, the area here represent uh, displacement of 50 meters from where it started, because it start from rest, so there's a zero here. I hope that's clear for the first part. Now, next, the car then travels with constant velocity for 500 meters for a period of 25 second, 25 second here. All right. So now is moving at a constant speed. So constant speed would be horizontal line, constant speed. Okay, for 25 second there. So roughly that is 25 second. And then I'm going to mark it down here. So for 25 second, let's assume that this is t uh, up to let's call that car then. Okay, vc. This is tc then. All right, now for 25 second, so this one will be tc plus 25 second. Now that is where the car is right now. And then for 500 meters, all right, now constant velocity for 500 meters. So the area under this graph here will be 500 meters. Before decelerating to rest, the magnitude of the deceleration is there. So the magnitude of the deceleration, it decelerate faster than its acceleration. So its deceleration is negative 2a meter per second, because it's deceleration, so its acceleration is negative 2a meter per second here. All right, until you come to rest. Okay, and then we have no idea when it come to rest, but we know that when it come to rest, the velocity must be equal to zero there. All right, now these are all the informations presented to us. We just have to make use of them um, to find out the next informations there, right? So before we move on to the next questions, just take a look at this graph one more time. This is how we sketch the graph based on all the informations given to us. So I hope this has been useful to your understanding. I'm going to move on to the next question shortly. All right, now I'm going to show it. I'm going to show the next questions now. It's much more easier in this way. Okay, let me see whether I have the next question. Okay, B. Now the next questions, find the value of A. Now we need to find the value of A. Where is the A? The A represent acceleration. Yeah, acceleration. Okay, let's try to find out. Okay, if you have no idea what is going on, you can always use all the available informations that we have. So first of all, we're going to make use of this first part of the informations. We know that the displacement is 50, acceleration, constant accelerations of a meter per second. So you can rely on the Suvet equation. So before we move on, I'm going to write down some of the kinematic equation. So, kinematic equation that you can find they can find out on the MF19 data booklet, right? Or you can actually memorize it. There's not much formula here. We only have like the first one here, V equal to U plus AT. Then next you have UT plus half AT square. And then maybe we can use the other one, V square equal to U square plus 2AS. Yeah, right. Now these are the main equations that we can use for any motion that is uniform acceleration. Okay, so let's take a look at how we can actually make use of these Suvet equations to help us to solve for the value of A here. Yeah, okay. That's the first one. Right. Now, I think the first one we are going to use V equal to U plus AT for this section here. I just mark down this section, the first section here. Using V, since I'm using VC here, I will write down VC equal to U. U is its initial velocity. Initial velocity was 0. Acceleration is A. It would have accelerate for a certain duration of time, and then duration of time is TC, and therefore we can simplify that as VC equal to ATC here. Now that's our first equation. We can't do much because we have two unknowns here. Now next, we also have the extra informations of 50-meter displacement, so we can make use of the you can make use of the second one, or you can make use of the last one. Doesn't matter. Since I start off by using TC, I might want to concentrate on using the second one. Now later I'm going to show you another way to obtain the answer without have to rely on the time itself. Okay, so here I'm going to use the displacement is 50. All right, now 50 meter, and then this displacement would be given by initial velocity was 0, TC plus half A TC square should be equal to 50 here. All right. Now you can see that ATC is here. ATC is here. All right. So from here we can actually rewrite this as half ATC multiplied by TC is actually equal to 50, because we have our ATC here. ATC is our speed itself. You can see that, all right? So from here, now let us see whether it's useful or not, all right? So from here, you have like, you can have, let me see what we have. You can actually have half VCTC equal to 50, yeah. But that does not allow you to figure out much of the missing value A there. So instead we can just write it down as second equation, for instance. Right. Now, at this point of time, you can always make use of these two equations that you have set up to just solve the equation. Now, we don't need the TC here, right? So we can remove the TC. Okay. Now, before that, just let me clean up these kinematic equations. We may not need it at this point. Okay. All right, now I'm going to clean it up. I'm going to write down at the side here so it's easier to refer. So by solving 1 and 2, all we need to do is just solve 1 and 2. I'm going to rewrite 1 and 2 out so that you can see what is going on. Okay, maybe not. In this case, I'll just take, yeah, depending on what you want to solve here. Take for instance, because we are not interested, okay, we can take 1 divided by 2, for instance. You can take equation 1 divided by equation 2. So by doing so, okay, hold on, I don't think 1 and 2 is a good choice. Maybe it's better we take 2 divided by 1 instead. Yeah, that will be much more better. All right, so 2 divided by 1, then that will be a TC will be equal to, so if this one divided by this, you only have TC on the left hand side, and then that will be 100 over A TC, 100 over ATC, and then therefore you get ATC square equal to 100 there. You can see that what we did here was not very significant. We actually go through a circle and then come back to the same equation, which is actually this 1.1. But anyway, it's a good learning curve to know that by manipulating these equations here, sometime we may actually reach the same conclusions that we got here. All right, and then we might want to devise another strategy for this then. Okay, let's give it a try. All right. All this while we have just make use of these two informations. It's not very useful. Let's look at the next informations and see whether it's useful to us or not. So since this is not very useful, but doesn't matter, it's a good checking point here. So I'm going to remove that. Okay, now we're going to move on to the second piece of information that we have here, which is 500 meters, the displacement. Okay, so we're going to use this 500 meter displacement. We don't know the VC for sure, but we know the time duration is 25 second there. So by looking at the second section, um, the displacement for this second section, I just call this S2 then. So S2 is given by 500 meters. And then S2 can be calculated quite easily because area under the curve, which is actually VC multiplied by 25 second. That should be equal to 500. And then you can get this quite easily. So we know that now the speed that it reached, the maximum speed that it reached is 20 meter per second. Okay, knowing this speed is 20 meter per second, we should be able to obtain from equations number two. So from equation number two is here, we should be able to figure out the TC. Okay, so TC will be 5 seconds. So this would actually take 5 seconds to reach here, and then this one will be 30 seconds. All right, and then VC that we have obtained is 20. All right. Of course, finally, we need to answer the questions. Find the value of A. Therefore, from equations number one itself, we would be able to find out A is basically VC divided by TC. So we have our VC as a 20, TC as a 5. So therefore, that will be a 4 meter per second squared there. All right. Now I hope that has been useful for you. Okay. Now the second way to solve it. All right. Okay. I'm going to pause here for a while so that you guys can digest these methods. Bear in mind, don't panic if the Suvet equations that you're using does not work smoothly. Always be persistent to see it through until the end. Yeah. All right. Now the second approach then. Right. Now let me clear this up. How do we use the second approach? Now I'm going to leave all these answer here so that we can use it as a reference. So second approach, instead of using, okay, now just let me rewrite this one more time. Kinematic equation. The more you write, the better you can remember this. So V is equal to U plus AT um, here, and then finally we have V squared equal to U squared plus 2AS. Okay, all right. Now, instead of using the first two Suvet equation, now I'm going to show you how we can make use of the first Suvet equation. So we're going to look at the displacement. For the first displacement of 50 meter, we can use these Suvet equations. We know that it reaches a speed of VC, okay, at the time TC here. Initial velocity was 0. We don't know its acceleration, of course, but we do know that the displacement is 50. Okay, so we can write that like this. So therefore, in this case, it will be 100 A. Okay, 100 A. That's our first equation. And then secondly, we're going to make use of our second information, which is S2 equal to 500. And then we know that S2 can be obtained by using VC multiplied by 25. And then of course that yield the same result there, which is 20 meter per second. Right. So by having this, we can substitute. So we can substitute our solutions from 2 into equations 1. So from here, we have 20 square is equal to 100A there. Therefore, the solutions for the value A would be 2 meter per second, just like what we have obtained. Is it? Oh, sorry, it's 4 meter per second square. Exactly the same result that we have obtained before this, but instead, previously we use A is equal to VC divided by TC, which is 20 divided by TC, which is a 5, and then that would yield the same result here. Right. Now, I hope that is clear. As I mentioned before, you can use many approaches as you like, because all these formulas are indirectly derived from the same source, so they should yield the same result here. Right. Now, I hope that is clear at this point. Okay. All right. Now I'm going to move on to the next section shortly. All right. The last sections for question 4. All right. Question C. Find the total time for which the car is in motion, which means we have to figure out the final time here. Okay, TF for instance, right? What is the total time of this journey here, right? So we have make use of the first part of the information and then the second part. Now we have not tried to use the last piece of information here. We're going to try to use all the informations that we obtained so far. Now, since we have obtained that the accelerations is equal to 4 meter per second, which we have already deduced that just now. Okay, so therefore this deceleration or this acceleration is negative 8 meter per second square here, which is the same as this. All right. Okay, now let's take a look at how to work this out. We know that this is 30. Instead of looking at that, just let me clean this up so that we can see this more easily. So this is 30, and then this part it will be TF here. So instead of writing there, maybe just let me clean this up. So TF here. All right. Now we know that the deceleration is negative 8. So for the last section, so we know that the deceleration, so I'm going to write down deceleration. Okay, so deceleration is given by the last part here is given by okay, since I'm using deceleration, so it should be 8 meter per second then. So I should be using acceleration instead, sorry. So accelerations for the last section is equal to negative 8 meter per second square. All right, now I hope that is clear. And then this acceleration can be given by the rate of change in velocity. So, and in this case, it should be based on this, it should be a 0 minus Vc divided by this time duration, which is Tf minus of 30. That should give us a negative 8 there. And then we knew about this Vc here, which is 20 meter per second. So I'm going to substitute that. That will be 20 meter per second Tf minus 30 equal to negative 8. Now, of course, the negative sign, you can simplify that. I'm going to show the working over here. It'll be much more easier in this case. So I will get Tf minus 30 is actually equal to 20 divided by 8 here. Or basically just 2.5. Therefore, the total journey time in this case would be the same as 32.5 second. All right, so I hope that is clear for the last section. All right, now I'll move on to the next question shortly. All right, welcome back. This is question 5. Okay, as usual, we're going to read that through. A block B of mass 4 kg. Okay, you can see that there is a block B, mass 4 kg, is pushed up uh, a line of a greater slope of a smooth plane inclined at 30 degree. Right now you can see that there's a 30 degree here to the horizontal by a force applied to B. So this is B here by a force applied to B, a particular block B here, uh, a force of F. Now acting in the directions of the motions of B. So B is moving this direction. The force is also acting in the same direction. Now the block passes through point P. You can see that the block passes through point P and point Q with a speed of 12 meter per second and 8 meter per second respectively. Now P and Q is separated with a distance of 10 meter, and then P below the level of Q. So P is actually below of Q here. Right now, the block has a mass of 4 kg. Here, I assume that the gravitational field strength G is equal to 10. So I'm going to write down my assumption here. I'm making assumptions my gravitational field strength on Earth, or for simplification purpose, is 10 Newton per kg. Therefore, the weight acting on the block is 40 Newton vertically downward based on this orientation. Okay, now before we get going, let me show you how the motion actually look like. So there's a force acting on block B here. As it passes through the point P, it has a speed of 12 meter per second. As it passes through point Q, it has a speed of 8 meter per second. Now we know that because there must be a loss in kinetic energy, and then this loss in kinetic energy is compensated by the gain in gravitational potential energy. Okay, and then by the way, since there's a force acting along the line PQ, there must be a work done to push the block B up to Q there. Right now, let me show you how the motion look like before we start to solve this. Okay, this is how it look like. Okay, okay, you can see that it's moving up. Okay, so initial speed was 12 meter per second, and then as it moved to the position Q, the speed decreases to 8 meter per second. Now I hope that is clear there. Let's look at how do we solve the first question. Find the decrease in kinetic energy of the block as it moves from P to Q. The decrease in kinetic energy. Now the usual case is we always try to find change in kinetic energy. So the change in kinetic energy is calculated using your final kinetic energy, your final kinetic energy, subtract off with your initial kinetic energy. All right. Okay. So your final kinetic energy will be half m, your final, and then subtract off with your initial. All right. Now we are looking at the change in kinetic energy as it move from P to Q. Now that would be, now since both of them share the same mass here, because it's the same particle, of course. All right. Now the final will be 8, the initial will be a 2. Okay. Now that will be a 2, -4, 20 there. Okay, let me see. So there will be a change of 160 joule of negative 160 joule of kinetic energy. Now this negative signify an or a decrease in kinetic energy. So therefore, decrease in kinetic energy is equal to 160 joule. All right. Now I hope that is clear at this point. All right. Okay, I'm going to move on to the next question shortly. Right, welcome back to the second section of question 5. Now, previously we have already found out our change in kinetic energy, which is negative 160 joule. Right. Now we are still looking at the same kinematics or the motion of this block B. Okay. Now the second question state that we need to find the work done by the force pushing the block up the slope as the block moves from P to Q. Right now, there are two strategies that we can apply here. So here I'm going to highlight the first strategy using conservations of energy. So conservation of energy state that energy cannot be destroyed or created, but it can be transformed. So therefore, mathematically, I can write down based on my consideration, I can say that total energy at position P must be the same as total energy at position Q because all the energy will be transformed to Q, right? So this is how I write down um, conceptually. So let's look at what energy do we have at position P. So we have kinetic energy. You can see that there's a kinetic energy. So half mu square. And then at the same time, since block B is located at a certain altitude from the ground itself, from the reference line, so therefore it also possesses gravitational potential energy, which is given by mgx. If I label this as x sine 30, should be equal to, as we move on to Q, all right, let's observe what energy does block B have at position Q. So I'm going to show you the simulation one more time. All right, you can see that it moved to Q, and then yes, it still possess a kinetic energy there. So we will have to include the kinetic energy, but at the same time, before we proceed with the kinetic energy there, I think I've forgotten uh, one more energy that I need to include here. So at position P, other than kinetic energy and gravitational potential energy, it also have work done performed on the block B so that the block B will have sufficient energy to move to Q there. So I need to include this work done. Sorry. So the work done to push the block from P to Q. Right? And then at position Q, we still have kinetic energy, and then we still have gravitational potential energy, of course. It's just that this time it will be x plus 10 because the distance from Q to the ground is x plus 10 here, sine 30, of course. And then that's all the energy that we have at position Q. All right, I hope that is clear. This is how we apply conservation of energy. And then from here, you will notice that the mgx sine 30, uh, we have mgx sine on this side, we have mgx sine on the other side also. So therefore we can cancel both sides. We have and then this is what we left with. Since we don't have x sine anymore, we only have 10 sine 30. And then from here, the amount of work done will be given by all right. So I hope that is clear. And then you do notice that this is actually change in kinetic energy. So change in kinetic energy is actually negative 160, which we have already found previously. And then now we just need to work out the change in gravitational potential energy. Now that will give us a 5. mg is just the weight. So that will be 200. So therefore, the amount of work done by the force pushing the block from P to Q is 40 joule here. All right. Now I hope that is clear for this. Now next, I'm going to show you the second strategy. Now the second strategy and the first strategy does not differ much here. So I'll just clear off this part here. Instead of using strategy 1, I will use strategy number 2. Also conservations of energy. I will also use the same sets of equations here. It's just that conceptually I will simplify it so that we can have another sets of conservation of energy that we can use instead of using this equation explicitly. So you can see that from here, instead of writing this, I can write this down as my initial kinetic energy. This is my initial gravitational potential energy, and then this is work done. This is my final kinetic energy, and then this is my final gravitational potential energy. Okay, and then all I need to do is just rearrange this. I will get my E1 minus E0 and then sum up with G1 minus G0 here. So you can see that this is basically change in kinetic energy. Final kinetic energy minus of initial kinetic energy is the change in kinetic energy. Whereby G1, gravitational potential energy, the final gravitational potential energy subtract with the initial, that is the change in gravitational potential energy. Right. Now the sum of change in kinetic energy and the potential energy would yield the amount of work done that you need to perform in order to overcome the gravity and to change the speed itself. So from here, we have found out the change in kinetic energy, which is 160, and then the gravitational potential energy, just now we have already worked it out, which is 200. Now, therefore, we end up with 40 joule amount of work done that is needed to change the speed, and then at the same time to increase its gravitational potential energy. Right? Now, I hope that's clear at this point. All right. Now I'm going to move to question 3 shortly. All right, section C of question 5 here. All right. Now we are still looking at the same setup. Okay, now the block B will move from position P to Q. The speed of the block B at position P is 12 meter per second, and then as it move up to Q, its speed decreases to 8 meter per second. Now C, at the instant the block reaches Q, the force pushing the block is being removed. All right. Now find the time taken after this instant for the block to return to P. There. Right. Now, first of all, we will need to figure out how far off the block B would actually move after Q. Right? Because once you remove the force itself, it would no longer have sufficient energy to further progress upward the slope. Therefore, there will be a position where it would reach the final speed of 0 meter per second. Okay, now let me illustrate that using a small simulations here. Hope it works. Okay, right now you have seen that I move to Q, and now you progress up, and then it would reaches 0 meter per second. All right, that is where it would stop here. Okay, that is where it will stop. I think at this point I forgot to remove this force here. So after Q here, the force has been removed. Yeah, bear in mind. Okay, so in my simulations, there's a bit of a correction here. So after Q, there is no longer any force being applied, and then as it progress upward, there will be a position where it will stop moving. So this final velocity will be equal to 0 meter per second here, whereby the force will be removed here. Okay, so I hope that is clear at this point. All right, now let's look at how to work with this. Now, first of all, of course, we will need to figure out like how far off the block B would actually progress upward until it reaches a final speed of 0 meter per second. And we know that at this position, it still have a speed of 8 meter per second there, right? Okay, I'm going to label this. The angle is still the same, 30 degree. Okay. So there are many ways to actually do this. You can either apply your conservations or energy one more time, which will be much more easier to work with at this point, I would say. All right. Or if you like to use your kinematic equations, that will also works in this case. All right. Now let me show you two strategies how we can work this out. Now first of all, by using okay, strategy number one again. Okay, conservation of energy. All right, conservation of energy. So by using conservation of energy, we are interested to find out how far off it would actually move upward. Okay, I label this as y then. Alright. Okay, so therefore, using conservation of energy, I'm going to write down the total energy at Q must be the same as the total energy at, I will label this position as R then, for instance. So total energy at Q must be the same as total energy at R there. So total energy at Q here. Let's this time instead of using this as a ground, which is a bit troublesome to work with, we will use this as a reference. Now bear in mind the reference ground is basically up to you to set up. So if you say that this is your ground, then therefore the only energy that you have that the block B have is kinetic energy. So I'll write that down as m u square, so which is 8 square in this case. And then since this is our reference ground, so there is no gravitational potential energy. And then when it reaches the position R, we know that its kinetic energy is totally zero, whereby it will gain gravitational potential energy, which is mg y sine 30 there. Okay, so from here we try to simplify this as m8 square equal to the mg is, yeah, just to make a remark here, is mg is 40 Newton, where the g is actually 10 Newton per kg there. So in this case we will have 40 y sine 30, which is the same as 20 y, because sine 30 is a half. So from here, this is 32m. Okay, 32m. Yeah, I forgot the m. The m is supposed to be a 4. So therefore, I'll write this one down as 4, 20y. Therefore, the y in this case, it will be 6.4 meters. Yeah, 6.4 meters. Right, 6.4 meters. So you will actually move upward 6.4 meter before it stop moving. Let's assume that it does not drop off from the edge, right? And then after that, it would actually travel down from here down here. So we are interested to find out how long does it take. Yeah, how long does it take to actually move it down? All right. Now that would depend solely on your Suvet equation now. Okay. Now the only challenging part at this point of time is of course the constant acceleration, right? So we're going to use the Suvet equations to find out the time here. All right. Now the Suvet equations that we're going to use will be, since we knew the y is 6.4, so the total distance from R to P, so PR now would be um, 16.4 meter. 16.4 meter. And then in order to figure out how long does it take to actually move down from here to here, we're going to use the kinematic equations. I'm going to write down here kinematic equations one more time. That will be v equal to u plus at, s equal to ut plus half at square, or v square equal to u square plus 2as. Okay, since we are interested in time itself, all right, so we can actually use this. All right, so use this distance. Okay, so we know that the distance is equal to 16.4. Our initial speed in this case, we start from r here. So r is 0. So this is 0. So there will be 0 multiplied with time. Half acceleration. Yes, correct. Acceleration is the toughest one. Just let me clean this up here so that we can see what we are looking at. The accelerations that we are looking at here is mainly due to gravity. You can see that the only accelerations acting on the object is in this direction, which is actually given by because this component is a g. So this component that contribute the gravitational acceleration is given by g. This angle is 30 degree, g sine 30. So your acceleration down the slope is g sine 30. And then would it always be g sine 30? Yes. If it's going down, it's g sine 30. If it's going up, it's a negative g sine 30. So here I'll write down g sine 30. Okay, that will be our acceleration. You can see that. And then multiply by the time square equal to 16.4. Alright, now that is quite easy numbers to work with. So that will be a 2.5. This is 5, 2. Is it half 5? Yes, correct. So it's 2.5. Is it 2.5? Let me see. 4. Yep, that's correct. So 2.5 t squared is equal to 16.4. And therefore, you can obtain the t there. Right. Just let me try to obtain the t here. Let's see what do I have here. Okay, 6.56 there. So it should be easy. 6.56 in it. Hold on, just let me check one more time, just to be sure. Alright, so after taking the square root here, you will get 2.56 approximately. So that is the time taken for the block to return to P. Alright, now just let me read through one more time to see whether this is the amount of time. Because in my calculations, the time t is the time taken from that position, the final position down to P there. Right. So based on the question, at the instant the block reaches Q, the force pushing is removed. Find the time taken after this instant or after this instant. Which means we have to include the time taken for the block to actually move from Q to the final positions there. So we also need to calculate that, which I miss out. Okay, let me include that. So I'll just call this T1 then. I need to work out the second part. All right. Now the second part is I need to work out how much time does it take for the block B to actually move from Q to here before it stop moving. All right. Now I'm going to use the same Suvet equations, which is S equal to ut plus half at square. All right. Now I have already found the distance there, so which is actually 6.4. The time taken to travel 6.4. My initial here is actually 8. And now acceleration, as I mentioned, if it's going up, right, it will be negative. It's going down, it will be positive. And multiply by t squared. Yeah, before I forgot that. Hold on, just let me clean that up. So let's multiply this, t squared equal to 6.4. All right, so from here I would indirectly get the quadratic equations. All right, so let me see, what do I have here? 2.5 negative, okay, negative 2.5 t squared plus 8t minus 6.4. equal to 0 here. Just let me see whether I can find a solutions to this. Okay, just let me try to use a calculator to try this out. Mhm. Mm, 5. Let me see what do I have. Okay, not an easy task. Okay, I'm going to pause here for a while. I'm going to work out the solutions. All right, now this is the quadratic equations that we have. So if you actually solve it using your calculator or anyhow you like, you can complete the square or find out the factor there. You should be able to obtain, based on the one that I have obtained just now, you should be able to obtain 1.6 second as the time taken to move from Q to the final position before it stop moving and then roll down again. Right? Therefore, the total time required will be given by T1 plus T2, and then that will be like 3 point. Is it 3 point? 4.1, 4.12, 4.12 second. Let me check whether that's 4 point. Oh, sorry, 4.16 second. 4.16 second. All right, and then there you have it. That's the way how we uh, use conservations of energy at the same time using um, kinematic equations to find out the total time taken to move from the top to the position P there. All right. I hope that is clear. This is using conservation of energy. So next, I'm going to show you how we can actually use kinematic equations solely to solve this without using conservation of energy. Right? All right. Second strategy. Strategy number 2. Just rely on kinematic equation. All right. Now I'm going to rewrite the kinematic equations again if you need it again. So we have V equal to U plus AT, and then V square equal to U square plus 2AS. All right. That's what we have. And then we have also deduced that the gravitational acceleration, if it's going upward, then it's given by G sine 30. In this case, based on the value of G that we are using, so therefore the gravitational acceleration in this case is -5 meter per second square. Right. Now I hope that is clear. We have all this. Now we can start to solve. Now first of all, we're going to look at the time taken to move up to this position, T1. All right. So to find T1, um, we're going to use these kinematic equations here. Okay, so we are going to find out. We know that V is equal to 0 in this case. So we're going to use this Suvet equation. We know that V is equal to 0. And then U initially was 8 meter per second. So I'm going to write that 8 meter per second here. Oops, I don't really need to include the meter, the units itself. Because it's moving upward, so therefore the gravitational acceleration is -5 multiplied by time there. So therefore T1, sorry. So 1.6 seconds. So it took 1.6 seconds to move up. And then now we're going to find out how long does it take to actually move from here down here now. Now, of course, before that, we wanted to find out the distance taken from Q to the top here. So I'll label this as R. So let's find out. We have to find the distance In this case, before we do anything, it's best to find the distance RQ here. To find distance RQ, you can make use of any one of these Suvet equations. For me, I think maybe if you have the time here, you might as well use S equal to U plus AT then. Since your U is 8, the time is 1.6. Now, of course, that would be half of 5 because acceleration is -5, time is 1.6 squared, and then that will be our distance. Okay, just let me try out one more time to see whether we get the same answer like before, which is 6.4, if I still recall it correctly. Okay, just let me try this out. So 12.8 here, and then this part here I will have, just let me see. Okay, so I have a 0.256 here. So therefore, let me see. So I will have 12.58. Something not right. Okay, so let me try this out and see what is wrong with this. Distance is the initial was 8, yeah. The time taken is 1.6, is half a, so the acceleration is negative. Time taken is 1.6, so therefore is 12.55. Something not right. Hold on, just let me check for a while here. What went wrong? The distance taken. Did I do something wrong here? It's 5. Just let me try out one more time in case I typed this wrongly. Oh yeah, I did type this wrongly. Sorry. Okay, so this is supposed to be okay, let's say M, right? Forgive me on that. It's supposed to be a 6.4 here. All right, so therefore this one will be 6.4. Okay, luckily. So exactly what we expected. So the distance traveled from Q to R is 6.4. Now therefore, we know that the total distance from R to P, distance from R to P will be given by 16.4 meters there. And therefore, we should be able to find out the time taken to move from here to here there, right, by using this Suvet equation. We know that the initial velocity is 0, so we will use 0. The time taken, the second part, because it's moving downward, therefore the gravitational acceleration is 5. Second time here. All right, so from here we will have T2 is equal to 16.4 divided by 2.5 square root there. All right, and then we should be able to get, just let me check one more time. Okay, whether it tally with the answer that we get. Yeah, it does tally. All right, so it does tally. So the second time is 2.56 seconds. Therefore, total time taken would be T1 plus T2, which is 1.6 plus 2.56, which is 4.16 seconds. All right, now you can see that you can either use your conservation of energy together with kinematic equations, or you can solely based on your analysis using kinematic equation. Right now, I hope this is um, a useful informations to your learning. Right now, I'm going to proceed on to the next question shortly. Right, welcome back. Question 6. All right. Now, again, we're going to read that through. A particle travel in a straight line PQ. The velocity of the particle t after leaving P is v meter per second, where v is equal to 4.5 plus 4t minus 0.5 t squared. Right. Now here we are going to find out the velocity of the particle at the instant when its velocity is 0. Now if you were to plot this graph velocity against time, you will see that it's actually a quadratic curve. Intersect at this intersection and then reaches this axis somewhere here. So I would say roughly the velocity is 0 at around between 8 seconds and 10 seconds there, right? Now we need to find out the velocity of the particle at the instant when the acceleration is equal to 0. Now we know that a graph of velocity time represent both the acceleration and the distance travel. So the gradient of this curve represent the acceleration. Now this is no longer a straight line or uniform motion. So therefore we have to apply a bit of calculus, uh, integrations and differentiation. So just let me write down the definition beforehand. Now we know that the acceleration Acceleration is given by the rate of change in velocity. So in calculus, we write it down as dv dt. In order to get the acceleration, we have to perform differentiation. So if you differentiate this, yeah, I hope that you still remember, the v is 4.5, 4t minus 0.5 t squared. If I were to differentiate this with respect to time, I will be able to obtain the acceleration, which is a 4 minus a t here, right? Now, at what time will the accelerations be 0? You can see that from the graph here. I would say maybe roughly, based on my drawing here, roughly you'll be at 4 seconds. And then the velocity will be somewhere like more than 12 meter per second. I'm not sure whether that's correct or not, but let's check out the algebra. All right, in order to find out when the acceleration will be 0, all you need to do is assign this equal to 0. Now we found that 4 minus t is equal to 0. Therefore, the acceleration will be 0 at time t equal to 4 seconds. But that's not what we want here. We are interested to figure out what is its velocity when its acceleration is equal to 0 there. So all we need to do is just substitute this one back into its original equation. So substitute t equal to 4 seconds into equations number 1. So from here we get 4.5 plus 4t, which is 4 minus 0.5, 4 squared. All right, 4.5, 16 here. Let me see. This is this is 16 also. It should be 8. 16 is 80 is 8. Yeah, correct. So this is 8. So there will be 12.5 meter per second. If I check through this graph, yeah, it looks like it's 12.5 meter per second. Just let me check one more round in case I always make mistake with my numerical computations. All right, 16 here. Yep, correct. Okay, so there you have it. That's the speed of the particle at the instant when the acceleration is equal to 0. Now, I hope that is clear. I'm going to proceed on to the next question shortly. All right, part B of question 6. The particle come to instantaneous rest at Q. Yeah, at Q. So we need to find the distance PQ. Instantaneously at rest means when the velocity is equal to 0 here. So it means that instantaneous, sorry, instantaneous at rest refer to v is equal to 0 meter per second. Right. So if you look at from this graph, this is where it reaches instantaneously at rest. So we can actually assign this 4.5 plus 4t is equal to 0 here. Right. Okay, so just let me try to see whether I'm able to solve this without any calculator. All right, now I would have now the usual way some of you might like to write like this. Yep, and then for me I don't like a negative sign, so I'll remove that. And then at the same time I don't like decimal number. Okay, seems to me like I can get a very nice answer here. Okay, now therefore the time taken is actually 9 seconds because the time must be greater than or equal to 0 second. So time cannot be negative, not at this point yet. So I will know that the time when the particle reaches instantaneously at rest is at t equal to 9 seconds. But how far is this distance? Like find the distance pq then, right? So now let's read through one more time. The velocity of the particle after leaving P. Okay, so after leaving P is given by this. So the particle come to rest at Q. So find the distance PQ there. Travel in straight line PQ. So okay, so what they are actually referring to is the distance here. So we want to find out how far it has traveled when it reached instantaneously at rest here. All right. So all we need to do is to find out the area under this graph here. In order to find out this area, now that would be given by distance PQ. Area is given by the integrations from let's assume that in this case it should be from um, 0 then. Okay, so from 0 and then until 9 second. All right, so the functions that we are integrating is this. All right, now that will yield the area under the graph which represent the distance itself. Now okay, or sometimes you will write down distance PQ is actually equal to the area under the graph. So from here we will get 4.5t 2t squared minus 0.5 divided by 3 t cubed, 0 to 9. Now of course we only need the 9 in this case, so just let me give me a while to calculate this. I didn't calculate this beforehand, so that will be 40.5 here. Okay, and then this one here, just let me try this out here. Okay, that will be negative 121.5, and then therefore I can sum up all this result. Oops, sorry, I think I messed up a bit. Hold on for a while. All right, so the final answer will be 81 meters, right? If they are using meters here, right? So the distance traveled um, by the particle from P to Q is given by 81 meters here, which is given by the area under the graph, right? I hope that is clear for this question here. I'll move on to the next one. All right, our last questions for today. Question 7. 7A, I think there are three sections here. Section A, B, C. We're going to look at the section A now. Now, before that, let's read that through. And now we have two particles, A and B, as shown in the diagram there. One of them is having a mass of 3m, the other one is 2m. Attach end to end to a light inextensible string. So the string passes over a fixed smooth pulley. The pulley is over here. All right. And then the plane is inclined at an angle theta here. You can see that to the horizontal. A lies on the plane and B hangs vertically as shown, 0.8 meter above the ground, which is horizontal. Now the string A and the pulley is parallel to a line of the greatest slope as shown in the diagram. Initially A and B are at rest. Okay. Now A, given that the plane is smooth, find the value of theta when for which A remains at rest. Okay, so because the plane is smooth, right now this is situations of equilibrium. So we're going to label all the forces acting on the system itself. Um, Now, of course, dividing and conquer will be the best strategy to use here. By dividing and conquer, I mean you have to observe the forces acting on each one of the particles. Okay, now let's look at particle B here. The force that is acting on B is its weight, of course. Now that will be given by 2mg, where we make assumption that G is 10 Newton per kg in this case. And then there is tensions acting here. Because the pulley is smooth, so therefore this part of the tension must be the same. This part of the tension must be the same. And then this particle also have a weight, so 3 mg in this case. All right. Okay. And then these are the component. So that's theta. I hope that's clear. All right. Now those are the forces acting. Of course, not forgetting there is also the normal force. If you want to include that. All right, there's a normal force. And then check through one more time in the exam, of course, all the forces, whether we label them correctly. If you are happy with that, then we are going to work with this. All right. Okay, so we are very happy with this. So by considering, we are going to consider this is where our divide and conquer strategies been applied. Consider forces acting on B. Consider the forces acting on B itself. Because they are in equilibrium, so therefore we know that based on Newton's second law, again this is purely Newton's second law, the resultant force must be equal to 0. Must be equal to 0 here, right? 0 Newton. Because they are in equilibrium, therefore we can say that T 2mg is actually equal to 0, and then we know that the tension must be equal to 2mg here. Okay, now of course that's not what we are trying to find here. Now next we're going to consider forces acting on A now. We're going to consider forces acting on A, still using the same Newton's second law. Right. Now, by considering forces acting on A is harder a bit, because in this case you wanted to consider the forces along the slope or perpendicular to the slope there. So we will consider the forces along the slope, along the slope. Or sometime I'll just write down this symbol along the slope. So along the slope, because it's in equilibrium, then we can actually write that down as T minus 3 mg. Along the slope, we have to resolve the weight into the slope component here. So that will be mg sine theta. So T, subtract off with this. This is a resultant force, must be equal to 0 because they are in equilibrium. Therefore, we know that tension is also equal to this one here. But we know that from number 1, tension is equal to 2 mg. Therefore, we're going to solve 1 and 2. So solving 1 and 2, we will have sine theta is equal to 2 mg there. Sine theta will be equal to 2 over 3. Now, getting the value for this would not be tough. All we need to do is obtain the inverse. Okay, give me a while. Let me see whether I can. It's an inverse of sine. Alright, now if I'm not mistaken, if my calculator is working properly, that will be 41.8 degree there. Alright, now I hope that is clear. Now, not only that, not only we stop here, some of you are wondering, can I resolve the forces perpendicular to the slope? Yeah, of course. If you resolve the forces perpendicular to the slope, that will be like 90 degree to the slope in this direction. Now, you will notice that there are only two components involved. We can conclude that R must be the same as mg. Oops, sorry about that. Must be the same as mg cosine theta there. And then since we have already found out our sine theta, so therefore you should be able to obtain your normal force acting on the particle A um, with respect to the slope itself. Right? I hope that is clear. I'm going to move on to the next section shortly. All right, second section. Right. It's still the same setup, but the second section is given by this question here, right? Let's read it through. We still have the particle 3m kg and 2m kg, particle B. It is given now, instead of the plane being smooth, it is a rough slope. The angle theta is given by 30 degree in this case. And then the accelerations of the particle A moving up the plane is 0.1. Now, knowing that as the particle A move up at the acceleration of 0.1 meter per second square, therefore B should be moving vertically downward at the same acceleration, 0.1 meter per second square also. Now, our task here is to show that the coefficients of friction between A and the plane is given as CERT3 over 10 here. All right. Now, let me show you a bit of simulation, how the motion actually look like. All right. So just let me label that first. So we still have the um, the weight itself. Okay, we still have the weight itself. Instead of having weight and there's no frictional force, now the slope is rough, so it must have a frictional force. Okay, just let me show to you how it look like. All right, you can see that that's how the particle A is accelerated up the slope there. All right, and then we know that there must be a frictional force down the slope. I just label as Fr, and then of course we have the weight itself. The weight is given by 3 mg. Now the same thing here, you have your normal force. We have the angle here, the same. And then now the same thing, tension. we also have just now we have a tension there. Now before it actually reaches the ground, we have the tensions there. Now of course this tension is very different from the previous tension, right? Because the object is accelerating. Previously the object was stationary, right? Now the same idea here, we get to consider um, each object separately. So we're going to consider B. Okay. Oops. Consider forces acting on B first. And then at the same time, we're going to use the Newton second law at the same time. All right. Now, knowing that, we have okay, because the weight of this object is 2 mg, and then because it's accelerating downward, its acceleration is 0.1 meter per second square. This is accelerating upward as a equals to 0.1 meter per second square also. Okay, so therefore, here we can write down 2 mg must produce 2 a here. So the resultant force produce an acceleration. Now the only mistake that students usually make, or I would actually make, would be the masses, because we are dealing with 2m. So it's better to change it to 2m. From here, um, we have our acceleration. So I think if you like, you can write down your tension, or we can evaluate the tensions quite easily, which is 2a 0.1. So that is actually 0.2 here. Okay, we also make assumptions that G is equal to 10 Newton per kg here. So that will be a 20 m minus 0.2 m. So that will be like 19.8 m there. Okay, now that's our tension. By consider forces acting on A. By considering forces acting on A along the slope. Okay, here we are saying all the forces along the slope itself. So here we can write down T subtract off with the downward component. Now in this case we have a downward components of the frictional force. We also have a downward component of 3mg sine theta, and then that would actually produce an acceleration 3ma here. All right. Now knowing that the tension is 19.8, so here I can write down 19.8 m frictional force, and then knowing that the theta is 30 degree, which is a half, so that is 1.5 um, 1.5 by g there, so it's easier to write 15 m there. It's equal to 3m 0.1. Okay, so from here we should be able to get let me see what we have here. We have 4.8. Okay, 4.8, so therefore FR is 4.8 m minus of 0.3 m. That would actually yield 4.5 m frictional force. Okay, now that is our frictional force. And then at the same time, other than resolving along the slope, we are going to resolve it perpendicular to the slope. So perpendicular to the slope, we know that R must be the same as 3mg cosine theta, because the object does not elevate or sinking, so it just stay on the same vertical component there, vertical position. So therefore, the normal force must balance out with the vertical component due to the weight. And then from here, we will have what we have here. We have 30m cosine 30. Cosine 30 is sec 3 over 2 here. So therefore, we have a 15 m sub 3. Okay, and then knowing that frictional force, because it's in motion, so therefore frictional force must be the same as the coefficient of friction multiplied with its normal force. Therefore, coefficients of friction must be given by 4.5 m, which is here, divided by its r, which is 15 m sub 3. And then let's see whether we have what we are supposed to have here. In this case, m can cancel off, so we have sub 3 1.5. So 1.5 by 1.5, and this is 1.5. Okay, just let me write down first. So 1.5 over 15. Okay, so therefore you actually have sub 3 over 10. That has we have managed to prove that the coefficients of friction is given by sub 3 over 10. Now I hope this Newton's second law is clear to you. We're going to look at the last um, quite challenging condition shortly. All right, our last sections for question 7. Okay, we still have the same setting. When B reaches the ground, it comes to rest. Okay, we can see that just now from the simulation. We need to find out the length of time after B reaches the floor for which A is moving up the plane. Okay, how long does it take for A to move up the plane there? That's our uh, main questions there. All right, now we're going to figure this out. Okay, let me show you a short simulation of how it actually look like before we attempt to work with this. Right? Okay, you can see that it start to hit the ground now, and then A will still move up. You can see that as it moved, as the B touched down, the string become is no longer taut. It become loose, I would say. All right, so it's no longer taut. But A will still proceed on with the motion. We still proceed on with the motion. All right, so that's how it look like. We are interested to find out um, the length of time after B reaches the floor for which A is moving up. So how long does it take for A to move from here, for instance, because this is the positions when the B touched down. So how long does it take for A to move up to this position before it stop moving? That is when its speed reaches 0 meter per second. All right. Okay. Now that is the questions there. Right. So I hope that is clear. Now before that, we need to know how far A has moved just now. A before that A was somewhere here, for instance. A has moved 0.8 because it's mentioned that B was 0.8. Before that B was here. So B moved down 0.8. So A would be moving up 0.8 to here. So our concern here is we have to find out what is the speed of A at this position. So we're going to find out the speed of A here. Right. Now knowing that the initial speed for A is 0 meter per second. All right. And then don't forget the deceleration because the object is moving upward. So I'm going to write it down here. We know that the gravitational acceleration is g, and then this is theta. So the negative acceleration is given by um, g sine 30 here. If it's going down, it's g sine 30. If it's going up, in our case, the A is moving upward. Okay, g sine. So let's consider the motion from point P to Q first. Let's consider this one from P to Q. Let's consider this. All right, where the PQ is equal to 0.8 meter. Okay, and then by using the Suvet equation, we can use Suvet equations for V square equal to U square, U square plus 2AS there, right? Now, our final velocity is here. I will write down UA square because this is our final. And then our initial here was 0 initially. Okay, initial was 0. And then what else? Let me see. Our final, our initial, and then our initial was 0. And then acceleration. Okay, so acceleration is given by g sine, and then distant move is 0.8. Okay, it's a plus here, sorry. So 2a sine, just let me check for a while. Moving upward. Did I get that right? Initially it was 0. Yep, correct. And then you will be able to gain speed here. So therefore acceleration should be here. Okay, I'm going to pause here for a while. All right, now we come to the last sections of this question 7. Right now, questions C state that when B reaches the floor, it comes to rest. All right. Now find the length of time after B reaches the floor for which A is moving up the plane there. Now we need to recall back again, the plane is rough in this case. And then initially, as the B moving down, A will be accelerating upward, B is accelerating downward. And then when the B reaches the floor, the string become slack. So just let me show you the simulation here. Alright, you can see that B reaches the floor, but A will still continue to move after the string becomes slack. Okay, just let me show you one more time. So by this time, when B reaches the floor, A would have moved 0.8 meter. So we're going to use this as our starting point. So when B reaches the floor, A would have moved 0.8 meter here. Initial speed for A is 0. And then we are interested to find out what is the speed of A at this point. Here. Okay. We know that when the string is still taut, both of these is accelerating. From the previous question, we are given that the string is accelerating, sorry, the object is accelerating at 0.1 meter per second square. This one is 0.1 meter per second square, right? So from here, we're going to consider the motion from of A from P to Q. Okay. By using kinematic equations, we can figure out the speed of A when it reaches position Q. So V square equal to U square plus 2AS. So right here, we know that V square, the U square is 0, 2A is 0.1, distant move is 0.8 here. So therefore, we have this is 1.6, 0.16 square root. That will be a 0.4 meter per second. So the speed of particle A when it reaches position Q as B touches the floor is 0.4 meter per second. 0.4 meter per second here. All right. Now next, the particle A will continue to move on. You can see that. I'm going to show you again. As the string becomes slack, A will keep on moving. Right. But for the second motion here, A will be experiencing a few forces. So I'm going to relabel that. Okay, I'm going to erase this. We don't need, yeah, maybe I'll use a different color so that it's easier to um, identify here. So you can see that there's a frictional force, and then there is a weight component, of course. Right. Now there's no longer tension in this case. We have the normal force. Yeah. Then we have the same angle here. Right. Now that's how it look like. So first of all, we are going to find out what is its acceleration when the string become slack. Okay. So string slack. So when the string becomes slack, we're going to figure out its acceleration. So what will be its acceleration? It will be here. There's no longer tensions acting. So we have 3 mg sine theta and then minus off the frictional force. And then acceleration. Okay, so accelerations would be 3 ma here. All right, so this is the equations that we are getting are from Newton's second law. F net is equal to ma. In this case, our mass is the 3 kilogram particle A. Right, and then don't forget that frictional force. Okay, so here let us simplify this. So that is sine theta. Frictional force is given by mu r here, and then r is given by, okay, so by resolving the forces vertically along the slope, so therefore we can get r is equal to 3 mg cosine theta. So from here we have 3 mg sine theta mu 3 mg cosine theta equal to 3 ma. So from here we can get our a acceleration. So that will be a negative g sine theta. This is 3 over 10. And then this is g cos theta. All right. And then, yep, the theta, just let me check. Yeah, if the theta, in this case, theta is assumed to be 30, like the previous question, given by the previous question. So our accelerations would be sine 30, a half, minus sec 10, g, and then cos is actually a sec 2 here. Therefore, we will get negative half g. What we have here is 3 over 20. So 10, that will be negative 13 over 20 g. Yep, I forgot my g here, which is negative 13 over 2. All right, so from here we know that the accelerations, or it is deceleration basically, so it's negative 6.5. So 6.5 meter per second square, right? It's decelerating, right? Now we have found its deceleration. Now we just need to find out how long does it take before it reaches another final velocity of 0 meter per second here. So we can apply another Suvet equation. All right, now take for instance the easiest one that we can use is v equal to u plus at. Okay, so from here we know that the final velocity must be 0. Its initial velocity should be 0.4. Acceleration is 6.5. Final is t. Therefore, the time taken will be 0.4 divided by 6.5 there. Okay, so just let me try this out. $6.5. Okay, so that would take about 0.0615 second. So the length of time after B reaches the floor for which A is moving up the plane is 0.0615 second. All right. Now the last one is a bit handy, so please pay attention to this question here. So I hope this has been useful to your learning. If you like what you are looking at, don't forget to press the subscription button and then the notification bell so that you can receive the latest video. All right. Thank you very much for watching. I'll see you again.